Hello, hello. Hello, hello. Yes. Okay. So welcome to lecture number 2. So the way I'll do it is first I'll introduce the lecture goals and then I'll get into the content. I know towards the end of last lecture we were a little bit rushed, but we can revisit some of the topic, some more details about that now. Okay. So I'm directly jumping to the lecture goals page. It's basically a link on the syllabus page because I want to come back to our goals that were there last time and and relate and then talk about goals for today. Okay. So last lecture, as if you have, since you were here or if you're not here, last lecture was mostly a review of machine learning. In particular, it's not really a review of all of machine learning, just one specific thing, which is prediction in the supervised learning setting, in particular classification in the supervised learning setting. And we saw a few things, key components. Okay, some key components that I wrote on the page, some components that I did not write. So the ones I wrote in my slide deck were what's the data, what's the model, what's the loss function, criteria for choosing something versus the other, and then finally the way to get to the best model. Okay, so think of really when somebody says model, they mostly mean a some function like a linear function or a random forest function or whatever it is with specific values in that definition. Okay, and when you say model class, linear function class, like the betas are like generic right now, standing right now, they will be specialized to specific values after you actually do the optimization. Okay, when people say model, they mean after you've already done the optimization, what is the some model candidate? You already have the model on which you can give an input and produce an output. Okay, so that was one of the key things from last time beyond motivation, and then we really towards the end, almost towards the end of the class, talked about chain rule or back propagation. For that, I think I mentioned in the class, and hopefully some of you were able to look it up in reviews or anywhere else. Like, what's the definition of a gradient? Okay, what's the definition of a partial derivative? In the slide deck, we said, okay, if you slightly perturb in, for one-dimensional case, if you slightly perturb the input, how much does the output change? Okay, that makes sense. And the same idea also work in the high-dimensional case as well. Okay, in the high-dimensional case, you call it partial derivative. In one-dimensional case, is a partial derivative same as total derivative? Okay, and the same as a gradient. Whereas in the high-dimensional case, a gradient is typically a vector, with each coordinate corresponding to how much the function changes if that coordinate changes a little bit. Okay, and so you should always think of gradient as being a vector, which is the same dimension as the parameter space that you are kind of optimized over. So if you are optimizing over a 10-dimensional parameter, let's say you're just doing linear regression or logistic regression, if you have 10 parameters, beta 1, beta 2, beta 3, and maybe beta naught, which is an intercept, let's say, you have 10 such things, then your gradient with a loss of, the gradient of loss with respect to these parameters would also be a 10-dimensional thing. And that's why you can do a gradient update. You can subtract from a 10-dimensional vector, some previous 10-dimensional vector minus alpha times another thing, which is essentially the gradient. So vector math works out. Okay. Anyway, but that was about gradients. But chain rule was really about, okay, if you want to find a partial derivative, or if you want to find the gradient of some quantity with respect to another quantity, you can really, if those two quantities are related by a bunch of computations, okay, bunch of transformations essentially, maybe a square, maybe a log, maybe an addition, something else, you can always draw it, at least you can draw it as a what is called a computational graph. And then you just have to worry about how do I take in that graph, since it's a graph, there'll be nodes and edges. Nodes are just going to be those basic computational units like an addition or a multiplication. And then you would just worry about, okay, what's the local gradient of that multiplication unit's output with respect to its inputs. Okay? As long as you know that, and that's not hard, as long as you know those rules of thumb, like, okay, multiplication, I know what the local gradient is, for addition, I know what the local gradient is, then you can just, chain rule just means multiply all those local gradients together. Okay. And backpropagation says, okay, multiply it in a nice way, starting from the endpoint, the last thing. You keep propagating those, accumulative things that are accumulating back, and then you'll get the gradient of the final quantity with respect to the quantities I care about. Okay, so that was chain rule. I'm sorry, I'm just using the Googles to kind of discuss this, but I will get to the slides. But I didn't want to. I want to at least mention this, what we're going to cover today. We will start with revisiting this multi-class logistic regression code base. It's just using NumPy, but still worthwhile to see, okay, that's the template of a code base which doesn't use TensorFlow, Keras, PyTorch, whatever. Because I think in the assignment, I think one of the last questions or something, they ask you to try out some nonlinearity stuff using Keras/Torch, okay, PyTorch. So, but it's still instructive to just see an example code. And then today we'll continue there, because multi-class logistic regression doesn't even work for a simple two-dimensional data. Okay, obviously you need to do something which is either feature engineering or increase the model complexity, make it nonlinear. We'll take the latter route. We don't want to do feature engineering much of this course, but feature engineering is a very good thing to do. Okay, so definitely, but it's not some new concept that we're learning. It's something you should do. You should try it out, because it's a very good, if you can keep the model simple but do feature engineering, you can keep some interpretability and really reap rewards. Okay, but we did not do such things, and so that's why logistic regression failed. We'll see that code now, and that leads us to the next set of goals for today, which is nonlinearity. Okay, making the model complex. Logistic regression, the model is actually just a linear model with some sigmoid transformation or whatever logistic transformation, and then ultimately giving us linear decision boundaries. So we need to make the model complex, and so for that, we need to make the model complex. So for that, we will add, we'll have a certain way of saying things. So we'll add things called layers, and we'll add things called nonlinearities. Okay, we'll get into what we add and how we define the model when we get there. That's the first part of the session today. We'll just kind of make our linear model nonlinear. Okay, and in that process, we'll talk about, okay, there's some new terminology that we're going to use, layers, nonlinearities, neurons, and things like that. But that's just new words for what's there. You can also say the same thing in English without using these words, but it's just a shorthand. But we'll do that. And then in the second half of the lecture, we're going to talk about, we'll start introducing one new architecture. I say architecture again, I'll define that, but it's basically one new model. Okay, another different function f, which is going to be nonlinear, but it will have a bunch of computations which we might not have seen if you're just doing 572 or 575. It's called a convolutional layer, and so there'll be slightly different computations. Okay, at the end of the day, they're all matrix vector multiplications here, but we'll see how that computation works out. Okay, and that's a very low-level detail. All I'm saying is today we're going to start from linear model. It doesn't work. That's what we saw towards the end of last lecture. We'll go to a nonlinear model, and then in the second part we're going to switch over and talk about a different nonlinear model, which actually again does the same thing. Don't do feature engineering, work with images, and because the way we specify this model, it kind of exploits the aspects of images and does well. Okay? So it's basically trying to do less feature engineering and trying to hide all that complexity in the model definition, if you want to think of it that way. Okay. And there are some technical terms. We'll talk about that when we get there. Okay, something called pooling also will be introduced towards the end of this lecture. Okay. Any questions here, like the trajectory? So last one was review and backdrop. Today is going to be a couple of model definitions, and rest of the course is also about also in a similar trajectory. Okay, so every lecture except for next lecture is going to be, here's a new nominal model, works with maybe text, maybe sequence of data, whatever, time series, for example. So for each types of modality, we'll kind of introduce a new nominal, new, I guess, prototypical model definition. Okay. Okay, so let's actually get to the linear classifier example. This is not the okay, I want to do okay. So this is something I just showed last time, where I was just showing how to like how does the data representation look like for a typical image, like a JPEG image that I downloaded. But let's not sidetrack there. So this is the example notebook that's available in the repository. So in our course repository, in addition to the syllabus page, lecture goals page, there is the assignments folder and the experiments folder. So yeah, examples folder. In the examples folder, this notebook, it's called linear classifier example. It's in the FFN subfolder. FFN just stands for feedforward network. Okay, but the acronyms, don't worry about it. There's a script like this. You can open it in Colab or Jupyter locally and just look at it, like how it's laid out. Okay, this is just an example from another course. So we just want to see how they've laid out what we learned from last time. Okay, so a bunch of imports. So we're just going to use NumPy. Again, this is just for convenience, matrix vector multiplication and so on. But you can actually replace this with any other linear algebra library. So you can actually use Torch instead of NumPy here. Okay, some directives. So this is where I think the Python aspect of the course is kind of important and is assumed. So if you're not familiar with Python, it's okay. We're not writing professional code here, but you do want to understand what each line is doing, right? So for example, this probably means this RC parameters is a dictionary, right? It says some keys where we're setting some values. Okay, you can always read the documentation of matplotlib to see what exactly that is. I mean, it's just setting some choices that we're making, okay, for the figures that we're going to plot. Similarly, other imports like what is pickle? Pickle is a way to serialize a NumPy object to disk. Okay, serialization just means this objects in memory as in like in your RAM. If you want to write it to disk so that maybe you turn off your laptop and next time you want to read the same object, it's easy to do that. Instead of like writing to a CSV file and explicitly f.open and then write something, instead of that, you can use the pickle library to do that. Okay, so let's actually see how logistic regression is implemented. Okay, this is literally when you import scikit-learn and import the logistic regression model and train on it. Obviously, it has a bunch of convenience functions for you, restraint splitting and other things. But here, this is how this is how you would write it if you just were given NumPy, for example, right? So here's the so first cell is kind of tangential. It's just generating this data. Okay, so obviously we are using some nice helper functions, np.linspace, which creates a bunch of numbers, according to the parameters here. How many numbers you want, between what ranges, and then it'll create a bunch of numbers. Okay, so I'm not going to explain this particular functionality in detail. It's just trying to generate this spiraling data. Okay, we want to focus on the model and the things that we saw. So this is the data part. Okay, so the 4 things that we saw last time. Data was generated this way. Okay, obviously, if you know the data generating process, you can do a lot. But generally, your data set is given. Somebody has already collected the measurements, and you can obviously plot it if it's low dimensional. If not, typically you would do a PCA or some type of an operation to kind of project things to low dimensions so you can visualize your data. Obviously, they may not be color coded. Obviously, if it's a classification setting, you may be able to add colors, but in general, you will try to kind of do some exploration with data first. So here, the data dimension is 2. and K is the number of classes, which is 3. That's why there are 3 colors. Sorry for the smaller actually usable area, but there are 3 classes here and 2-dimensional data. Okay, so this is where it departs a little bit from the notation that we used in the slides. Okay, how do we, how are we departing? We are actually making the number of rows to be the same dimension as the number of features, and number of columns to be the number of classes. Okay, remember in the much of discussion in the last lecture, we were thinking of, okay, if it's a 3-class classification, I'm going to get 3 scores, right? And so I was thinking of 3 scores. Generally, whenever you think of a vector, always think of a column vector, unless specified otherwise. So, but this W matrix is just the transform of that. Okay, and why did we write the transform of transpose of it and not the version that we saw in the slides? Yeah, is because of vector multiplications. Vectorization that we'll see. Yeah, go ahead.
0.01 always the vector used to multiply, or
no, you can remove it and see what happens. It's just scaling. So np.random.random produces numbers between 0 to 1. Okay, and this is just a way to say, oh, I don't want numbers between 0 to 1. I want numbers between 0 to 0.01. But why do you need these numbers? This is a good point. It doesn't probably have too much effect in this loss regression case, but it will have some effect in when you're training really deep networks. So the word deep means there's going to be some functions which are going to be complex, and we'll get there in a few minutes. But this what we're doing here is just called initialization. Okay, and so this 0.1 has 0.01 has no significance right now, but it will become significant later. Yeah, sorry, I don't know if that clarified your question, but it's not useful right now. You can choose anything. You can choose 1. You don't have to have this multiplication. Yeah, so here we're just initializing. Okay, what could be? Remember, we were going to do gradient descent, so we need to start with some old values and subtract some scale version of some alpha times the gradient of the loss with respect to the parameters, right? So I need to start with some values. I'm just starting with some random numbers in this 2x3 matrix, and I'm going to start with some random numbers, in fact zeros, in this 1x3 vector. Okay. Any questions here? It's just starting with, okay, I need to do gradient descent. I have the data. My model is going to be f of x is equal to wx plus v. It's just that we have just transposed it. So instead of think of it as f transpose of x, or call it f nu of x, which is just the transpose of it. So x transpose w plus v, if you want to transpose. So the transposition is just for some efficiency reason, and I'm going to mention that in a second. So we have that lambda parameter. That was a hyperparameter. We said, okay, we can choose it using cross validation. Here is just, for illustration purpose, we just chose it to be some value. Ideally, want to wrap it up in a cross validation loop, and that's something a helper function in scikit-learn can do it nicely for you. You don't have to write it explicitly like this. I mean, we haven't even written it here. I'm just saying that if you want to do cross validation, you can write it. It's not here, or you can use scikit-learn's cross validation helper function to do it. Okay, so here's the initial value of w and b, and then here's my data, right? So remember, so in my data, in this example, we have 300 data points. Okay, 300 rows. If you want to think of it as a tabular data, 300 rows and 2 columns, 2 features. And so x.shape, since it's a NumPy array, it will show you that, okay, the first coordinate has 300 and the second coordinate has 2 columns. So that's the number of examples. So we're going to choose some step size. Here it says 1. Okay, again, the choice is why is it 1, why not 0.01, why is it not 100? Those are things that you can try out in this code. Okay, and you'll see for large values of step size, you'll not be able to descend on that loss surface. Okay, remember for loss regression, the loss surface, when I say surface, for every w comma b choice, there's some loss value. If you can imagine w comma b as like a 2D plane, it's not exactly 2D plane because clearly there are 9 numbers at 9-dimensional thing. But if it was a 2D plane, then the loss surface is actually like a bowl. Okay, it's exactly like a bowl, so you can actually get to the bottom of the bowl if you can do gradient descent with reasonable parameters. Okay, so step size is an important reasonable parameter. If you choose it too large, then instead of going down, you might be going elsewhere. Okay. Okay, so this is just a number of iterations of gradient descent steps. So in each step, what do we need to do? Somehow we need to compute. In each step, our goal is to get to new candidate values for W and B, right? And at the beginning of the step, we have all values of W and B, and we started with something like random numbers, right? So that's the objective. We want to somehow go to new from old, and the hope is that the new values lead to lower loss or lower quality metric values. Okay, score. So the reason W was chosen to be the transpose was for this vector operation. Okay, so X, remember, is 300 cross 2. So I wanted to multiply every example, simultaneously with W. Okay, since every example in this capital X matrix is a row instead of a vector, I had to transpose my W matrix so that it multiplies correctly. Remember, my linear model is WX plus B, but there the X is a column. Here, every example is a row, so I just have to transpose it, which is also a transformation. So this is the forward pass. Okay, people use the word forward pass, and we'll see the name appear again and again. Forward pass means given the current values, if you start the current values, give inputs which are training inputs right now, what are the scores you're going to get? Okay, so you got scores. Take the exponent. So this is again a vectorized operation. You're basically np.exp is operating on every single element of this scores matrix. Okay, scores matrix actually has 300 rows and 3 columns. Okay, remember the 3 classes. So scores is actually a matrix because it's just simultaneously computed. Okay, so we're taking every score cell in this 300 cross 3 matrix, and this just taking e to the power x, e to the power x operation on it. So e to the power every score value. Okay, so we just so after that we are doing again a vectorized operation. So we're computing probabilities, which is we're taking all these scores and dividing by the row-wise sum of scores. Okay. How are we doing row-wise sums? We are calling np.sum with axis is equal to 1. So it's taking the scores, this exponentiated scores matrix, and then taking a row-wise sum, and that's the denominator. And so every element in the exponentiated scores is getting divided by that denominator. Okay, I'm going slowly here. I know it's a little bit boring, but if it's not, then it's okay. But if you think it's super slow, then I can speed up. Is that fine? Okay. So, so once we get the probabilities, remember our logistic loss, cross entropy loss, softmax loss is all the same thing. That focuses on for the actual label for this data point, what is my probability? Okay. So we need to we need to compute the negative log of among the 3 numbers that I generate for each example. I want to know for the actual label what is the probability I'm generating. So how am I doing that? Again, this is a vectorized operation, and that's why it's not, if it was not vectorized, I would not spend much time on this. But how are we doing that? We are just saying, okay, take the probability matrix. Again, this is going to be a 300 cross 3 matrix. Each row, probability of being in class 0, probability of class 1, probability of being class 2. Okay, 0, 1, 2, because Python is 0 index. Those are the 3 classes in our data set. Okay, so each row has the probability of class 0, 1, and 2. And so, but for that each row, we actually know what class that row belongs to, or what that data point belongs to. Okay, because we have 3 classes: the blue, the yellow, and the red, probably, right? So the y is actually a vector. Okay, it's a vector which is 300 length, and it's a vector, so 300 length, and each coordinate either has 0 or 1 or 2 value in it. So it's just saying, okay, among for this row, pick the appropriate cell in the probability matrix. That's what we're doing. So it's a vectorized operation, just to kind of give you a flavor of how you can do it in NumPy. And that's the log probabilities that you want to pick, and then you just take a sum of them. Okay, you can take sum, and then you can divide by number of examples if you want, or that's just for normalization. That doesn't really affect much. But you're just taking sum of these log probabilities, negative log probabilities. Okay, that's your loss. And then similarly, the regularization loss is here they're doing the L02 loss. So W times W. So if you do it this way, then it's going to be element-wise multiplications. Okay. So the first, so W is a matrix. So first cell of W is multiplied with first cell of W. Second cell of W is multiplied with second cell of W, and then you're doing a sum operation on that resultant thing, and then you're multiplying with the regularization parameter. Why this 1/2 or 0.5 is for, again, convenience. You don't have to add it, but if you don't add it here, then you have to take into account that the gradient has an extra factor 2. If you've done the assignment already, remember, if you have y is equal to x squared, then the partial derivative y with respect to x, or whatever, total derivative y with respect to x is equal to 2x. Okay, so the 2 factor has to be accounted somewhere else. We are taking a 0.5 here explicitly so that the 2 and the 0.5 cancel, and we don't have to worry about this here. Okay, but this is a minor detail. And loss is the loss on data and loss on your preferences, which is our preferences, L2, any model, anything which has low L2 loss here. Remember, we are only taking L2 on W matrix and not the B. And why this choice? It's very similar to if you have an intercept in linear regression, generally you don't try to regularize the intercept to 0. Okay, you don't try to put, okay, you don't include it, for example, in your in your ridge regression, you don't generally include the intercept. Okay, because if you wanted intercept to be 0, you are actually preferring a linear fit which goes through the origin. Okay, that's a strong preference. I mean, so if you don't want to import that, then you kind of leave the intercept out. Okay, that's what we're doing here. And so that's the forward path, actually. I mean, to get to all this from here to here is just for the current old values of W comma B, tell me what the loss is. Okay, that's just computation of loss given all the parameters. Now is the interesting part. We are doing a vectorized version of backprop. Okay, so it's basically in 2 steps. Okay, what we're doing first is computing the gradient of the loss with respect to the scores, and that's what is called D scores in this script. Okay, it turns out gradient of the loss with respect to scores. Remember, scores is a 300 cross 3 matrix here, and loss is one number. Okay, what is the gradient of the loss with respect to 300 cross 3 matrix? It should also be a 300 cross 3 matrix. Okay, that's just, I told you, right? Even for vectors, gradient should be the same as the thing that you are trying to take the gradient over or take the derivative over. Now, this 3 lines are basically trying to do a vectorized version of what should be the gradient of loss with respect to the scores. And the gap from scores to loss is just that scores have this e to the power transformation going on, and then the appropriate negative log of the one of the score value is being taken to be a factor in the loss value, right? So those 2, that's the forward pass, and so the gradient is gonna turn out, and we're not gonna do it in real time, but we can do it maybe after the class. Is that the gradient of the loss with respect to scores is exactly the same probability matrix, except whichever in every row, whichever is the true class, you subtract -1 there. It turns out that way. You don't. It's not a rule of thumb. It's not. You don't need to memorize it. You actually hand derive what is the gradient of the loss with respect to like the 3 score numbers. It just turns out to be the same as the probabilities, except the probability for the true label just has a subtraction of -1. It just turns out. Okay, it's pure. It's just mechanical. And that's what's being shown here for the scores where it is a true label, you just subtract -1. And there's also this divide by number of examples is only because loss had a divide by number of examples here. Otherwise, that would not be there. Okay, so that's the key trick. It's not really a trick; it's just mechanical. That's a local gradient of the loss with respect to scores. Now, what is the local gradient of the scores with respect to W? Okay, remember, scores are nothing but x times W, right? So the first line here, scores are nothing but appropriately take care of dimensions, but np dot x comma W, right? So the gradient of scores with respect to W is just going to be x. Okay, that's what you'll see there. So it's x, but x transpose. Okay, it's not exactly x; it's x transpose. And then we take the incoming gradient, which is this gradient of the gradient of the loss with respect to scores. That's the incoming gradient times the local gradient is the gradient of the loss with respect to the W parameters. Okay, so in this step, we are just taking the incoming gradient with the local gradient and just multiplying them together. Okay, and why is this an NP dot and why not exactly? Why in the class last time we just did a one-dimensional simple case. Okay, with A, B, and C and a simple function. But if you vectorize it, this is how the local gradient is multiplied with the incoming gradient. Okay, and similarly for B, which is the other parameter, its local gradient. You saw local gradient is just 1, right? So local gradient of scores with respect to B is all ones. Okay, so all ones times the incoming D scores. Just like it's like saying I have 3 score numbers. I have all ones vector. If you just multiply them together, it's like adding up the scores. Okay, for example. So that's what we're doing. With axis is equal to 0, we're just adding up the scores. Okay. Any questions here? I mean, I know this may look. I mean, we are towards the end of getting to that mu is equal to old minus gradient. Maybe these steps, I think you can play around and see mathematically whether they work out. In fact, in the assignment, you have the second question where you'll do it for a much simpler problem, which is y is equal to mx plus c. Very encouraged to do kind of maybe not maybe exactly like this. Very encouraged to try out. Okay, what is the local gradient of y with respect to m? It's going to be x. Okay, what's the local gradient of the loss, which is let's say mean squared loss with respect to y? It's going to be 2 minus 2 times something, right? So it'll exactly mirror what we're doing here. Okay, and lastly we have to add the two. So the loss is actually not just data loss, but data loss plus the regularization term. And if you take the derivative of the L2 thing here, it's a square, like something like x squared. So 0.5 times regularization times x squared. If you take the derivative with respect to it, then 0.5 and 2 cancel. So it's like regularization times x. Okay, that's what's happening here. So that's we're just saying, okay, whatever is the gradient we got plus the regularization times w here. Okay, and that's it. So all his effort here was to explicitly capture. Sorry, this line onwards was to explicitly capture what is the gradient of the loss with respect to w and loss with respect to b. Okay, once you got those two quantities, we're just doing a gradient update here. Okay. Yeah, I mean, at least the structure should be clear now. Thanks to PyTorch or Keras or TensorFlow, or there are many other JAX and many other packages. You don't have to, if you know this template, you don't have to do these steps explicitly. Okay, there's some function calls you can do, so you can get the gradients behind the scenes easily. Okay, gradients with respect to any quantity and any other quantity. Okay, and then you can, and even this step, these two lines that you're seeing here, even those you don't have to explicitly write it. Okay, you can just call depending on this is just called gradient descent, right? So batch gradient descent or whatever, stochastic gradient descent also is another word with some some extra detail. So you can just call it, let's call it optimizer. Optimizer the step will exactly do this step operation, this subtraction operation. Okay, we'll see that in the next class when we see an example PyTorch script. So that's it, and then we ran the script. This is how apparently like the loss came down. It's not too low. But that's because of certain reason. We are using a linear model on this very non-linear looking data. And so there is a very bad practice here of just saying x test is equal to x. You should not do that. This is just for illustration. Just showing in-sample fit here. Okay, I mean, ideally you should not care about, you should look at in-sample fits, but that's not the only thing you should focus on. Okay, so model diagnostics was the point missing in the last lecture's review. In addition to data, model, whatever optimization and loss, you have to worry a lot about model diagnostics, whether the model actually makes sense, whether it's, are there some outlier examples and all that. That's an art in itself. It's not a mechanical thing, but that's a very important thing. But anyway, if we did in-sample like testing of quality, then you could just say, okay, how what are my predicted classes in-sample? In-sample just means I'm using the same data on which I fitted the model, right? So here's the plot, and this code is just plotting things. Again, you may want to look up how it's plotting because we are using contour F function. So that requires a certain gridding of the data, and then at every point you kind of evaluate the model and so on. But let's ignore that plotting part. So this is how it looks. Okay, so you see that it seems very unlikely that you can reduce the loss further because there is no way to have a linear decision boundary and and get away with classifying this data better. Okay, so this is the example where we left last time. Any questions? Okay, there are no questions. Then we'll jump over to the slide deck, and we'll actually revisit that same example with the nonlinear function that we'll see now. Okay. Recall what we're trying to do now in the first section is just go from linear to nonlinear because a linear model was not good. Okay? That's the high level trajectory we are on. Okay. So I'll skip the first few slides which are about Python. I assume everybody has some exposure in Python. If not, I think it's very hard to learn both Python and deep learning at the same time. It'll be good if you kind of get up to speed with Python in a different class like 572 or 575 or something. Okay. Let me skip over that details. Yeah, so as I said, we're gonna have in this lecture two parts. First is the point number 2. We're going to make our function nonlinear, and then the point number 3 we'll consider in the second half of the lecture. So let's now start. Let's now start improving the model class. Okay, so we have this linear model that we load last time. F of x, w, and b is wx plus b. Right? So linear transformation of x plus some offset. Okay, that's why it's a linear model. Now what we're going to do is introduce a new model called the feedforward neural network models, which will have some nonlinear transformations. Okay, nonlinearity is just a way to refer to nonlinear transformations. In that, if you think of a computational graph, a bunch of computations happening. If you think of this function's computation graph, there's a bunch of computation happening, multiplications, additions, whatever. But at the end of the day, the transformations are linear. Okay, linear transformations mean if you have x shifted by some quantity, then the transformation would be exactly Okay, let me properly say this. So if you evaluate x at some point, and if you evaluate x at another point, then and whatever scores you got, if you take a linear combination of x, like some middle point between the original x and the new x, then essentially in the scores dimension also you'll get some same middle point. Okay, so it's just linearly decomposes is another way to refer to it. I just gave an informal definition of what linearity is, but you can look up Wikipedia if you want. Okay. So we're going to introduce this new model, which we'll call it as a 2-layer model. So layer is now a new word in addition to nonlinearity. We'll spend some time on both of these words in the next few slides, but here's a model definition. Okay, so we just want to, in this slide, we just want to match. Here's the original linear model. Here's a new model definition. What's changing? Okay, so this new model has, first of all, 2 additional parameters, W2 and B2. So that's why the first set of W and B's, we just call it W1 and B1. Okay, so now we have 2 pairs of W comma B's. Okay, now how's the function itself? If you just ignore everything else, how does the function define? It's just saying, okay, take x, multiply with W1, add B1. Okay, I'll get a bunch of numbers, right? I'll take a max of 0 and those numbers. So max of 0 and those numbers. So think of let's say here it says W1 is d cross q dimensional. Actually, W1 is q cross d dimensional. So this is off here. Okay, so just one correction here. W1 is q cross d dimensional. So W1 times x plus B1 is going to produce a q dimensional vector. Okay, so max of 0 on that q dimensional vector is going to be every coordinate of the q dimensional vector. You're going to say, oh, is that number greater than 0 or not? If it's greater than 0, leave that number alone. If it's not greater than 0, substitute a 0 over there. Okay, that's all. So max of 0 comma that vector is an element-wise operation, very similar to the np.exp function that we saw in the code. np.exp on a vector or a matrix is going to be an element-wise operation. It's just going to, every element you're going to just do e to the power something. In that code here, for every element of the incoming vector, you're going to do 0, compare 0 with that. Okay. So you're going to compare that, and that's where the nonlinearity is, and we're going to spend some time on that. And then the resulting vector is still q-dimensional, and that vector we're going to multiply with another like matrix W2. Remember, W2 is, again, this is also flipped, p cross q dimensions. Okay. So W2 is multiplied with the resulting vector. This whole thing results in a vector. So W2 times that vector plus the B2. It's like saying, okay, I had the original X, I did some linear transformation, which is Wx plus B, but then I did a nonlinear transformation, which I'm going to talk about soon, max of 0 comma that resultant vector. And then whatever resulted, I'm going to do again a linear transformation with the W2 and B2. Okay. So I'm doing a two-step linear transformation. Linear transformations, when I say linear transformations, I think of Wx plus B. Okay. I'm doing it twice, one after the other, but before doing a second linear transformation, I'm doing a nonlinear operation of which is basically element-wise max of 0 comma its input. Okay. So we'll spend time on that nonlinearity in a second. But these dimensions should match, so these things are transposed, so this should be changed. Okay. Any questions here? So this is the definition of a feedforward neural network, and we'll spend some time on what is nonlinearity, what is a layer, why is it called feedforward neural, why is it called even a neural network? And so all those things we'll kind of revisit again and again. Hopefully, here this slide is just saying what's the difference between the original function and this function. Any questions? Any challenges? Yeah.
I mean, I was just gonna ask what you said this is the definition of feedforward, but you doesn't explain that. So,
No, I'll explain each of the words that are alien looking right now, like nonlinearity, layer, feedforward, neural. They're all alien right now so far, right?
Oh.
I mean, we might have heard of these things elsewhere, but all of them are kind of new. So we'll kind of revisit some of these in the next slides. But here I just wanted to focus on, this was the original function we've been talking about up to now, and this function looks almost the same, but except same transformations happening twice, but there is a nonlinearity in between. Nonlinearity isn't like a nonlinear transformation happening in between, and in fact that leads to the next slide, which is what is nonlinearity, right? So nonlinearity is just a, they could have just said a nonlinear function. Okay, what is a nonlinear function? Is just remember what is a linear function? It scales. If you take some combination, if you had x, let's say x1 and x2, I think I just told you the same definition before. For x1 and x2, if you apply a transformation on it, okay, and then sum them together, you get some result. If you add x1 and x2 and then apply the transformation, then you'll get the same result. That's another way to say something is linear. Okay, it's like saying, so for example, y is equal to x is a linear function. Why? Because if y is equal to x, then if I take x1 plus x2 and apply nonlinearity, apply this function, which is an identity function, then I just get x1 and x2, x1 plus x2, sorry. But if I apply this identity function on each one of them separately, I still get whatever x1 and x2, and if I add them, I'll still get x1 plus x2. So identity function is a very bad example here. But for example, the previous page, why is this a linear function? Is because I can apply wx plus b on x1 and wx plus b on x2 separately, and then add them together. Okay, I'll get some resultant scores. I could apply wx plus b on x1 plus x2, and I'll get a bunch of scores. Those scores are the same. Okay, it doesn't matter. It's just that's just one way to interpret like what a linear function is. Okay, so but in this table, nonlinear functions, to differentiate from them, are functions where so that property doesn't hold. Okay? But in simpler terms, these are all one-dimensional functions on this page. So it's easy to visualize this nonlinearity. Okay, a linear function in one dimension is just going to be a function which should look like y is equal to x or y is equal to alpha times x, where alpha is any real number. Okay, or in fact, y is equal to alpha x plus beta, right? So that's a linear function. So every other function, so y is equal to alpha x plus beta is going to be some line, right? So in 2D plane, it's going to be some line with some slope. It could be, going down, going up. It's a line. Okay. All these other functions are not going to look like a line. Okay. So they are all nonlinear functions. Okay. And we're just calling them nonlinearities because we're going to use these functions element wise somewhere in that forward pass. As in when we go from feature vector to scores, somewhere we're going to use these functions, or one of these functions, for example. Maybe not all the functions. In fact, some of these functions have names just because of historical precedence in signal processing and other areas. So sigmoid is this function 1 by 1 plus e to the power minus x, and we'll see the functional form in a second. Visually why it's nonlinear, we'll see that, but you can probably guess that it's nonlinear. Similarly, you can guess that these things are also nonlinear. Okay, so this function max of 0, x or x, 0, it's called a ReLU function. Just stands for rectified linear unit. Okay, so some of you have done electrical engineering. There's something called rectification of waveforms, but it's basically related to that. Okay, that's the precedence. So these are all one-dimensional functions, and we can see that in the next slide. So there's so many choices. In the previous slide, we made a choice when we showed that new function. We said, okay, we're going to use max of 0, x. Okay, why not something else? Okay, now this is a point where I want to disclaim that all these choices that people make in defining neural network architectures, most of them are empirically made, in the sense that they observe some good properties. Maybe they can optimize well. Maybe the function really, captures the data patterns well, and therefore fits the, it gives better performance. So based on those choices, based on those observations, some of these choices are made. Okay, so why not? For example, ReLU and not sigmoid? There's just much of it is based on empirical evidence, but sometimes there's some, I would say, intuitive reasoning of why maybe they should prefer one versus the other. Okay, so let's actually look at each of these functions. So sigmoid, it's the simplest one. This is something that you've seen. Sigmoid function is exactly the logistic function as well. So this is clearly nonlinear, right? So if you take two inputs, apply the sigmoid transformation, you're not going to get the sigmoid transformation of the sum of the inputs. Okay, so it's actually a value between 0 to 1, irrespective of its inputs. Okay, inputs can be anywhere between minus infinity to infinity, but its output is always going to be between 0 to 1. Okay? So we know, I mean, if we go back to the backdrop page, we know how gradients work, right? So if this nonlinearity was in some network, was in some model, okay, then what will happen is, at that nonlinearity, you can think of that as a node in your computational graph. Somewhere, remember, we are going to use it. If we use it, then it will also have its incoming gradient, and it will have its local gradient, which is, let's say, if its immediate output is z and its immediate input is immediate output is g and immediate input is z, then this term on the left is the local gradient, right, or the partial derivative of g with respect to its input. This is going to multiply its incoming gradient, and it's going to flow back. Okay, that's what's going to happen, right? The moment we introduce these nonlinear functions somewhere, their local dynamics is basically just this: whatever incoming gradient, their local gradient, and then it goes up, right? So it turns out, because of the structure of this function, you can see that, beyond, let's say, -6 and +6, it's actually already reached, in the case of -6, it's already reached 0. So it's not going to vary much whether it's -6 or -7. Okay, which means that the local gradient here in this region is going to be essentially 0. Okay, the output is not changing much with respect to its input. Similarly, in this region, the local gradient is going to be 0 again. Output is not changing much with respect to its input. Okay, so if that is the multiplying factor to its incoming gradient, that means, you put in a ton of effort, you learn that, okay, there is some, gradient of whatever, loss with respect to some scores. But then if you apply this transformation somewhere, then it's going to kill that gradient essentially. Okay, because of this multiplication, right, while going back. So if you have these old values and you have new values, but then because of this extra factor in your chain rule, your gradient of loss with respect to parameters is 0, and so your old parameters are not changing to new parameters. Okay, obviously this doesn't happen always. It only happens when z is like a large value or a large positive value or a large negative value. When I say large, I'm not even talking about huge numbers. I'm just talking about 10 and -10. Okay, So that is potential issue with this nonlinearity, but people still use it, and in fact we will use it in a model class called LSTMs later. Okay? We will still use it. And also, I mean, another property is not zero-centered. You can always make it zero-centered by maybe subtracting by 0.5, for example, but it's not zero-centered. Okay, typically. And why does it matter? Maybe, I mean, so there's no intuitive kind of explanation here. It's just that empirically people observe, slower convergence. And this convergence is the number of steps needed in your gradient-based procedure to get to some optimal value, get to the low loss value. Yeah. But that's an empirical reason. But these are at least the properties of this nonlinearity. If you use this nonlinearity, these could be potentially, these are properties, they could be an issue, they could lead to some issues. Okay, let's look at tanh. Tanh is very similar. In fact, tanh is not just dark color, it's actually the dashed blue line here. So it exactly looks like a sigmoid. Okay, so don't focus on the red and the green, focus on this dashed blue here. So it again takes a value between minus infinity and infinity and produces a value which is between minus 1 and 1. Instead of 0 and 1, the sigmoid was producing a value between 0 and 1, it's producing a value between minus 1 and 1. Okay. The same issues, gradients vanish if its input is minus 10 and 10, gradients will vanish. Okay, but at least it naturally fixes the zero centering problem. Maybe it'll improve. In fact, again, this nonlinearity we're gonna again revisit when we talk about this class of models called LSTMs. Okay, so it's not completely like there's one best nonlinearity and everything else is kind of not useful. People try to experiment with this. It's just a question of you are defining. You're a model designer. You're gonna choose some things. Some of these things are not intuition driven. They're driven mostly by performance, but some of them are intuition driven, and that's what we want to capture, the intuition part. The empirically made choices. That's kind of hard to justify beforehand. Okay, now let's look at the last one, which is ReLU, which was the max of 0, x. That was the one in the example 3 slides ago. So this function looks like this. So this blue curve here, the bottom, only focus on the blue one, not the green. So the blue is the max of 0, x. So obviously x is positive, then it looks like a straight line because in that region y is equal to x. Okay, whereas when x is less than 0, then y is equal to 0. So here it's just the blue line is flat when x is negative. Okay, so that's the nonlinearity because clearly it's not a linear function. Linear function would be like y is equal to x throughout. Okay, so it at least doesn't have vanishing gradient problem on the positive side because it doesn't matter if the input is 4 or 40, the local gradient is still 1. Okay, which is nice. At least it's not like killing the gradient, as in diminishing the gradient value. But on the other side, on the negative side, because of nonlinearity, the local gradient is 0. Okay, so it comes with both the positive and a negative thing. But it's empirically observed to do well, at least in feed-forward neural networks, and that name I'll revisit again in a couple of slides. So this where like the third point is basically interesting nuance point leading to his question about why did we use 0.01 in that code, like initializing W values, right? So that's where I think it slightly plays in, is because depending on your initialization, what if all the Z values are negative? Okay, then you're like in forward pass, you're basically doing a max of 0, negative number, you'll get zeros. You're basically getting some corner case, all the scores are kind of off. Okay, maybe 1/3, 1/3, 1/3 or something like the transformation scores. And also backprop also will not work because that local gradient right now is 0. So there are situations depending on the initialization of your W on your data set that your gradient descent is basically not going to work. Okay, so it's a little bit nuanced. So something else has to also fail so that things match here. Any questions? So this is about nonlinearities. We only looked at one term that we introduced in the example slide. Now let's talk about layers and neural part there and so on. Okay, let's come back to that feed-forward neural net that we introduced 3 slides ago. Okay, so I wanted to first put all terminology together. So there's some extra terminology in this slide. So this function is just called a feed-forward neural net. Okay, why? It's because it's a bunch of stages of linear transformations. Okay, so if a neural network is completely defined by these stage-wise linear transformations, then essentially it's called a feed-forward neural network. Okay, that's just a choice that the community has made to call this function class. Okay, so as you can see in the bottom, there's a linear transformation in one step, and then some nonlinearity, and then again a linear transformation of whatever is the resulting thing. Okay, so W2 times what I called I guess activation vector plus B2. Okay, so there's two-step linear transformation happening, and those are only things happening here. That's why it's called a feed-forward network. Okay, feed-forward neural net. Okay, now why do we call it a neural net? Because these, if you think of drawing a computational graph, okay, this is not really a computational graph. This is just an illustrative, looks like a computational graph, but not exactly a computational graph. But if you draw a computational graph, every node in that computational graph, you could kind of relate it to a neuron type of a computation. Now that's a stretch, and we'll do that stretch, in a couple of slides. But the neural part comes from that. Okay, relating the computation that's happening in some sort of a computational graph to a neuronal computation. Okay. Net is just because it's it can be, this function is just a bunch of matrix multiplications with some nonlinearity, but you can actually draw it as a graph. Okay, and the graph, a graph, another name for a graph is a network. Okay, when people refer to a network or a graph, it's kind of the same thing. Now, so that's where the last part comes, the network part comes in. Okay, now why does this look like a graph? So here's the graph actually for this particular function. So here what we're drawing is the input, the intermediate quantity after doing the linear transformation, and final quantity after doing the second linear transformation. Okay, so the two linear transformations lead to two vertical placements of these nodes, these circular things, which in a graph they are called nodes, and then we also represent the input as one extra set of circular things. Okay, so this layer view is this view is what leads to the word layer. Okay, so you can think of you can call this vertical collection of circles as an input layer. You can call this intermediate outputs that were generated along with the matrix associated with it. You can call it the hidden layer, and the outputs, the collection of outputs, like for example the scores, along with the matrix that led to it, you can call it the output layer. Okay, so it's just we started with this function. We wanted to give it a graphical picture. We gave a picture. It's not exactly the computational graph that we saw in backdrop case. Okay, last lecture. It's not exactly the computational graph, but it's a proxy for imagining how computation moves from left to right. Okay, left to left part would be like the input. Okay, here's how input is getting processed stage wise. Okay, and each stage, as I said, is a linear transformation. That's why we call it a feed-forward network. A neural part will evaluate these circular things kind of look like neurons in some way. We'll make that kind of analogy in a couple of slides, but that's how you're getting some extra words here. Okay, one of the words is this function is called a two-layer network. Okay, two layers because there's a hidden layer and output layer. There's also an input layer, but we don't really count it. If we do represent it in diagrams, but we don't count it as a part of that network terminology. So we'll call it a two-layer network or a single hidden layer network. Okay, so how many hidden layers are there? There's only one, so we just call it a one hidden layer neural network. Okay. Layers are just these collection of circles, and the circles are supposed to represent those intermediate computations that we're doing, intermediate vectors. Obviously, input vector is just input vector, we're not doing any computation, but the hidden layer is supposed to kind of represent the intermediate computations, the intermediate outputs that were generated. Okay, what are those intermediate outputs? You can think of them as either Wx plus B, those collection of numbers, or you can apply the nonlinearity and then call the resultant collection of numbers the output. Okay, so the hidden layer output is actually, you can think of it as the output of this max of 0, W1 x plus B1. Okay, and these circles are called nodes, and nonlinearity is is not shown here, but it will, it's going to result. It's going to be part of computing this hidden vector or hidden result. Why is it called hidden? Hidden because it's not something that is important to consider while computing scores or loss function or anything. Okay, it's just something. It's an intermediate quantity, so we're just calling it hidden. Okay. Any questions? I think some words are again will be revisiting, but nonetheless, if some word is completely not covered, let me know. Okay, so so as I said in the previous slide, this feedforward network from that we saw example we've been seeing for the past few slides. It's called a two-layer network, okay, two-layer model. The number of layers is essentially, as I said, related to the number of linear transformations. Okay, so W comma V pairs lead to the number of kind of nomenclature here. And right at this point, you can say, okay, first of all, even with linear, at least in the linear model case, in the logistic regression case, there was not too many choices. The input dimension was fixed, so the matrix had like one dimension fixed. The output dimension was fixed, so the matrix also had a number of rows fixed. So there's not much choice to be made in terms of anything. Okay, so W and B were kind of fixed because input was certain size and output we only had 3 classes or whatever. Okay, here there are some choices. Firstly, what is the dimension of W's and B's involved in this two-layer network? There's some flexibility. Okay, in particular, how many okay, there are 2 questions. So let's focus on the second question. How many hidden units? Okay, so the first linear transformation that we're doing is a W1 matrix. How many rows should it have? You can choose, number of rows to be 100. It doesn't matter. As long as that, if you choose number of rows of W1 to be 100, then the intermediate, the hidden layer output will have 100 coordinates, right? So hidden vector will have 100 coordinates. As long as you can go from 100 coordinates back to your 3 coordinates that you wanted, the 3 scores, you're fine. So as long as you choose W2 to be 3 cross 100, then you're good. So the 100 is now a choice that you need to make. Okay. Similarly, the question is why only stick with the previous example where you only did 2 transformations? Why can't we do one linear transformation, apply the nonlinearity, another linear transformation, apply the nonlinearity, another linear transformation, and so on? You can do it like 10 times. Okay. How many times should you do? Should you only do it twice? Should you do it 10 times? There's a design choice again, right? So, right, even at this point, without introducing other things, there are some choices to be made. And how do people make these choices? These are mostly rules of thumb in the community. Really depends on how complex you want to make your function. Okay, the more layers you add, as in more linear transformations with lot of nonlinearities, the more complicated that function is. Okay, complicated just means that it can represent all sorts of decision boundaries. Okay, compared to if you make the function only 2-layer or even in the extreme case, no hidden layer, 0 hidden layer network is that original linear function that we saw. Okay, because it only has one linear transformation, no nonlinearity, and no second transformation. So that's a 0 hidden layer network. Okay. Let me skip a couple of slides. These are relating to the backprop thing, which there's no specialization here. It's just repeating the same thing for the feedforward network. So now actually I want to go back to the example. I don't know if it has been run. Oh, it looks like it has been run. So let's just directly jump to the result, and then we'll come back to what changed in the code. The code is exactly the same as the code that we went through in the beginning of the class. Okay, except a few changes. Obviously, the model is different. There's 2 transformations, so we have to take care of that. So here's the fitted model on its own data. Okay, this is not something you should be showing because, as I said, X test was the same as X train and Y test is the same as Y train. So you're just showing ensemble fit. Obviously, if we choose richer and richer models, you can fit better. But here is the decision boundary, right? It's clearly nonlinear. The red portion is delineated by these nonlinear boundaries here. Okay, so this is the delta you got by enriching your model space by keeping everything else the same. Okay, your data is the same, optimization, objective, all of them. So from logistic regression to feedforward neural network model, both are producing a bunch of scores. Both will undergo those logistic transformations like e to the power sj divided by some of e to the power sj thing. and both will have an cross entropy loss. So everything else, loss function, optimization technique, data is the same. What changed is the model class. Okay. Okay, so what changed? I will not go through all the backdrop and forward prop steps. Sorry, forward propagation steps. Yeah, but these are the two steps. Let's at least show the model, right? So model is basically saying, take a linear transformation. This is exactly the same as the previous code, right? Do an np dot maximum of 0, comma each of those numbers that we get, and then that collection of intermediate quantities, they get multiplied. They again do a linear transformation, which is, you can do it this way. You can also use some shorthand notation to do this, but these are the two linear transformations with a nonlinearity in between. Okay. Any questions? Okay. So let's look at this page. This is actually a nice web page. Everything behind the scenes is running in JavaScript, right? So so here's an example, right? So this is your different data set, not the spiraling data set in our example. This is here's the data set, right? So you can choose 4 different data sets here. Actually, let's choose the spiraling one. Why not? And we have 2 features, just like in our code. Okay. And here's the examples. You can choose a lot of things. Learning rate is exactly the alpha that we saw in the gradient descent update, right? So you can choose, I think in the code we chose some high value. There's no need for activation because there's a logistic regression. You can see that x1, x2 directly kind of lead to some decision boundary here. So there is no activation needed. Regularization, let's choose whatever we did in the code. I don't know if these are the numbers, but it's okay. We'll do this. And let's do classification. Okay, so here actually you can run this and you can see what is the loss, and actually not much is happening because your loss, test loss and train loss are almost the same, 0.4, and in fact your decision boundary is right here. And you can see the gradient going from blue to orange. Okay, so you can see that if you wanted to draw the decision boundary, it would be some line like this. Okay, in this 2-dimensional space. There are 2 classes here, right? So let's stop that. Now let's introduce one hidden layer. Okay, since we introduced one hidden layer, this is a one hidden layer feedforward neural network or a 2-layer feedforward neural network. Okay, it's all the same thing. Now here's the choice, right? The moment we introduce one extra, this hidden stuff, hidden layer stuff, we need to choose how many hidden units we need to have, right? So here they said, okay, let's use two neurons. Let me just make it 6 neurons. Okay, so neurons just mean that what is the dimension of this vector that you want to have? Okay, the number of rows of W1 basically. Okay, so let's say we choose 6, and then activation. What was that? ReLU, right? So now let's I guess just run it, right? So you can see that now decision boundary is somewhat nonlinear. Let's actually pause this, increase the learning rate, or maybe not that high, but okay. Okay, I'm not getting a good choice here. Okay, all these are you can see actually from this diagram that these other, because of nonlinearity that we use, these are actually not effective. Okay, this is exactly the issue that I was talking about with the max of 0, x. If your numbers are negative, then you're kind of off. So let's actually pause it, change it to sigmoid nonlinearity, and then this is a particularly hard data set. Maybe we should add a few more layers. Okay, this is a hard data set. I'm gonna just use something else. You should be able to see nonlinear decision boundaries appearing easily. I mean, I'm not going to play around here to show that how it works, but you can. So you can play around. I mean, this is very similar to playing around in the Python code, but here, in fact, you can see that this is worse than the previous linear model. So I would encourage you to try, playing around with this during the break, which I would suggest we'll take now. And let's get back at 4:52. Okay, so you can play around with this. It's just playground.tensorflow.org. I think it's also linked on the lecture page, the lecture goals page, so you can just try it out. Okay. And then we'll now shift gears and do something else. Okay, so let's resume. So feedforward networks, there's actually not much more to them in terms of core ideas. It's literally a bunch of linear transformations with some nonlinearities in between them and new terminology to say, okay, here's a layer and here's a node and a graphical representation of it, right? So on playground or tensorflow.org, you could try the logistic regression model as well. Like without hidden layers, it's a logistic regression model. It actually also shows you how, if you do feature engineering, if you remember x1 and x2, you can do extra choices on that page, and they're essentially feature engineering. If you do that without even hidden layer, you can still fit nonlinear addition boundaries, right? So you can do that as well. So I'll encourage you to do that. And it's really cool to see a full-fledged neural network in the browser. Okay, it's a nice piece of technology. Okay. Any questions about feedforward neural networks? Yeah.
Is the number of features versus the number of layers kind of like complementary to each other?
Number of features versus number of layers.
More of one.
No, they are. I think they're orthogonal because even if you have the number of features to be high, it doesn't tell you whether you should use less number of layers or not. Okay, think of a 1,000-dimensional feature vector. Now, in that case, should you use a 1 hidden layer neural network or should you use a 10 hidden layer neural network? It's a priori unclear. Yeah, in that web page, they show linear transformation, so they show extra features so that you don't need layers to achieve nonlinear boundaries. But that's linear models are versatile that way, right? Linear models are not limiting because if you do a ton of feature engineering, you're actually in reality you're in a higher dimensional space where it's linear, but in the lower dimensional space you actually are nonlinear, right? Right? For example, if you have two features x1 and x2, let's say you add another feature x1 times x2, and you add another feature square root of x1, and another feature log of x2, let's say. Okay, now you have a 5-dimensional space. In that 5-dimensional space, you're still searching for a linear addition boundary, right? If you stick with linear models. But if you project that 5 dimensions back to 2 dimensions, because x1 and x2 were the only starting points, right? It would be a nonlinear addition boundary. So sticking with linear model space by doing a ton of feature engineering will get you pretty complex addition boundaries. Okay, and that's what I think in lecture 1 I showed you ImageNet performance, right? ImageNet classification task up to 10 years ago, right? 12 years ago, which is actually not much in technology space, right? Like if you think of mechanical engineering or electrical engineering, the technology is like 100 years old. Just 11 years ago, SVMs plus feature engineering were giving you really complex decision boundaries between 1,000 class image classification, which is amazing, right? So yeah, I would say a priori there's no relation between number of features versus number of hidden layers you want to have. In fact, maybe if you have a really high dimensional vectors, as in high dimensional input features, maybe you need more complex functions. Okay. Yeah. So as I said, feedforward neural network, there's actually not much more to say about them. But they can be hard to train, and you saw me trying to train and they did not work with the choices I made. Even feedforward neural networks with just 2 or 3 hidden layers are hard to train. So you can imagine there's going to be networks that you'll see which will have 1,000 layers. Okay, how do you actually train 1,000-layer network some people have figured out what are the right regimes of choices to make so that it actually works. But many of the networks that you will see are actually hard to train. And so when people actually come up with new language models or whatever, they put in a ton of effort to be in the right regime, so actually minimizes some loss and actually generates good text, right? Or whatever, ChatGPT or Claude or whatever those models are. So they put in a ton of effort. So it's not easy, but there are rules of thumb that they follow. They do observations, they try something, they're completely off, then they'll say, okay, in this regime or these weights, they need to be initialized in certain ways. So initialization also influences those things. Okay. So what we'll do next is we'll look at a different. So we'll start introducing a new model. Okay, this is a model that is kind of depart from the linear regression stuff or logic regression stuff that we've been seeing, and also therefore departs from the feed-forward neural network that we have been seeing. But it's a good example of a situation where you're not going to do feature engineering, but just because the way you define the model, like whatever the linear transformations are, for example, it naturally takes into account some aspects of especially images. That's what we're going to focus on, and that's good. Provides good performance on classification or whatever we're doing. Okay. We'll stick to classification narrative for now. So that's called a convolutional neural network. Okay, and we explained. So we were actually, before getting into convolutional neural networks model definition, we'll kind of talk about neural first, because I think we did not talk about neural last time. So let's do that. This slide is actually a summarizing slide, so let me skip that and talk about neuron. The why called neural there, right? So in a feed-forward neural network, given a vector x, we transform it to a score vector, right? So that's what even a linear regression model was, logic regression model was doing. But in feed-forward case, we pass it through a sequence of hidden layers. Now, each hidden layer, we're going to now start using the terminology. Each hidden layer essentially composed of neurons. Okay. So what are these neurons? Let's say the hidden layer corresponding to the matrix W1 produced 100-dimensional vector. Like let's say the number of rows of W1 in our example was 100. Okay, and then we're going from 100 to 3 class, let's say. Then W1 is producing 100-dimensional vectors, which are hidden vectors. We're going to talk about, since it's producing 100-dimensional vectors, we're going to call each of the coordinates to be a neuron or neuron's output. Okay, so we're going to say, since we chose the hidden layer, the number of rows of W1 matrix, which corresponds to the hidden layer, we chose the number of rows to be 100. We're going to say that this hidden layer has 100 neurons. Okay, so the number of neurons is the same as the number of coordinates of the vector that you're producing at that layer. Okay, and so we're going to say, okay, each hidden layer has neurons, and each and the number of neurons is the same as the vector length. And now each neuron for a feed-forward neural network, and this is an important property that we're going to revisit again, is fully connected to the previous layer. Okay. Now, what do I mean by that? So you can think of each neuron. So the first output of the linear transformation. Remember, the first linear transformation related to the hidden vector is W1x plus B1. Right. Let's focus on the first coordinate. Right. The first coordinate. How did we get that? We multiplied the first row of W with the X column vector. Right. So that output or whatever, that neuron's output is related to all inputs, all input coordinates. Okay, that's the statement. That's the statement. Each neuron is fully connected to the previous layer. Now, if we talk about the output layer, that is also corresponding to a matrix W2 and the vector B2. Now, output, let's say it's a 3-class classification, then we have 3 outputs: score 1, score 2, score 3. Score 1 is fully connected to all the 100 outputs from before. Okay, so all the 100 neurons of the previous layer, of the hidden layer. Okay, so in feed-forward neural networks, every coordinate is kind of influenced by all the outputs of the previous layer. Okay, that's how the last statement is saying. Okay, so which means that every coordinate is associated with one row of your W matrix related to that layer. Okay, so for example, the hidden layer, that let's say one neuron, let's say the topmost neuron, is related to weights, which are the the entries in the first row of the W matrix. Let's call it W1J, W2J, W3J, and so on. Okay. So these are all the weights related to the same neuron, and they get multiplied with x's. I mean, x1 to xn. Let's say there are n coordinates of the input. Each one gets multiplied with its weight, or basically that's why we're using the W matrix. W, we're going to use the word weight as well. I didn't explicitly call it out, and then they're going to get summed, right? So it's literally remember, a row vector times a column vector is just take the first coordinate, multiply, take second coordinate, multiply, add them all together. That's pictorially being shown as x1 multiplies with w1, x2 multiplies with w2, and so on, and then they all sum together. Okay, that's all it's being shown here. And then there is this sum is being okay here. This threshold is basically one of the coordinates of the B vector. Okay, remember, if your hidden layer has 100 neurons, then there is going to be a B vector, which is also going to be 100 dimensional in length. And so the first neuron has the B1, for example, as an input to it. Okay, so that B1 is being is the second incoming arrow. So there are two incoming arrows. One is the sum or X transpose W, whatever that inner product is, and then is a B, and then there's an activation function. Here is a Greek letter phi to represent that, but you can just think of this activation as like nonlinearity. Okay, nonlinearity is also called an activation function. Just I know we are introducing a lot of nomenclature here, but as you kind of progress this course, you will see the same names again and again and again, and you will get comfortable. So bear with me for a second. And so this P, you can think of it as max of 0, x for now, if you want to think of ReLU nonlinearity. Okay, and then after doing that, you get an output at that neuron, which we call the activation of that neuron. Okay. So yeah. So now this computation is called a neuronal computation, or at the level of each neuron, is because this kind of resembles an actual, not resembles, I mean, that's a stretch, but it's similar, analogous to how in brain in a human brain, right? So a neuron is connected to multiple other neurons through synapse connections, and you can think of at least in the biological brain, things get triggered. They'll start triggering other neurons, and the trigger happens when some sufficient potential is reached or something like that. Some incoming triggers happen, right? So it's analogous to it in a very superficial way, and that's why the terminology neuron was borrowed. Okay, but this is the reason why there's a neuron or neural in the name. Any questions? Okay, so now so that was just the explanation of neuron. Now we're going to start getting into this convolutional neural network. It's a new model definition, so it's just the same F, but the definition is going to be looking different. So let's start with the feedforward, and then slightly more, we're going to start modifying it to get to this new model definition. So previously, this one hidden layer neural network, feedforward network, these were the connections. So basically, each neuron, the reason why these edges, the 3 edges going into the first circle, is because you can think of the first circle here as a neuron, and therefore it's connected to all the preceding inputs. So x1, x2, x3, let's say in this diagram. And similarly, this neuron here is connected to all of its preceding inputs. Okay. So this is how you would visualize it. So this is how you visualize the connections. Okay. Now let's start. We're going to start with that previous diagram and start modifying it. But I wanted to also kind of ground one data set at least. Okay, ground in the sense that represent what is the data set we could be working with for this model class. Okay, because previously X was just a vector, and we were like, okay, some matrix vector multiplication is happening, Wx plus B. But now we're going to depart from that and start talking about images. Remember, last time images were 3-dimensional arrays. So it's like 3 matrices on top of each other. Okay, so here's the data set. It's called CIFAR 10 data set. 10 corresponds to the 10 classes that are present in this data set. And it's pretty small images. Okay, 32 cross 32 cross 3. is the size of each image. Okay, so there's 32 pixels in height, 32 pixels in width, and then three such matrices, each matrix corresponding to the primary color, intensity of the primary color. Okay, so that's the size of each image in this data set, and here are just some, I guess, 8 examples, oh no, 10 examples per class. Okay. So, I mean, so first let's motivate why we need a different architecture. First of all, is because if we were thinking of feedforward neural networks, they would obviously give us nonlinearity. So they would give us this 10 class classification problem, let's say we want to focus on, then they could give us nonlinear decision boundaries between, you know, each of these 10 classes. But the first fully connected feedforward neuron would need to have 32 times 32 times 3 weights. Okay, if you remember, the image has 32 times 32 times 32 times 3 numbers. If we just vectorize it, so huge. I mean, this is like whatever the number, you know, 30 times 30 is 900 times 3 27, you know, 2700 numbers, right? So 2700 numbers, that means one neuron in the hidden layer, let's say it's one hidden layer feedforward neuron, one neuron has 2700 numbers. Okay? Now we have 100 neurons. Now you have 270,000 numbers, right? So times 100, did I do it correctly? Yeah. No. Yeah. 27,000. Right? Okay. 27,000. No, I said 2,700. 27. Yeah. 20. What did I say? 270K, right? What I got the first time. So 270,000 numbers would be needed for just the first hidden layer transformation or the first linear transformation. Okay. Obviously, you get to choose the number of hidden units in the first hidden layer. Maybe you choose it to be small, let's say 100, 100 or 1,000. Then the next, depending on how many score vectors you generate, in this case 10, then that each of those would need to see those 1,000 odd neurons in the previous layer. Okay, so the number of parameters is huge, even for the small images that we saw here. Okay, so these are really small images, and for that we need so many numbers, 270,000 numbers. Okay, now what if the image is actually somewhat realistic, a megapixel? So this is actually the resolution of like a really low end laptop, 1280 by 800 or 1280 by 900, for example, and already here just like 10 to the power 6, right? So 1,000 times 1,000, 10 to the power 6 numbers for one neuron, a million numbers for one neuron. What do I mean by million numbers? Remember the W's, one row of the W matrix. Okay, that's a million of them. And now if you have whatever, like 1,000 such hidden units or hidden neurons, then 1,000 times a million is a billion numbers right there. Okay, so you're now really going up by a huge amount in terms of the number of numbers needed to store to actually do gradient descent on. Okay, now you're really computing a gradient of loss with respect to a billion numbers is too many. Okay, so yeah, a score vector. It's just this vector. So these functions that we're seeing so far, the f is equal to wx plus b, the function evaluation, let's call it f of x. That is we're just calling it a score vector. Is the vector of numbers which are right before getting transformed into probabilities and then getting plugged into the loss. Yeah. Yeah. Anybody else? Any question? Okay. So think of score vectors as right before doing the logistic transformation. Okay. Okay. So what we're going to do now is to deal with that complexity. Okay. We although feedforward neural networks give us nonlinearity, they kind of need too many parameters. The W's are, by the way, parameters, and they're also called weights because for historical reasons. But basically, they're just parameters of the model definition. Okay. Now, what we're going to do is start motivating because of that huge numbers of numbers that we had. We're going to start to kind of reduce them by starting with let's start with a layer point of view. So let's start with that feedforward neural network and try to do something with it. Okay. before we kind of reduce the number of numbers, we're going to rearrange these hidden units. Okay, so we remember in the previous slide we put the orange circles one below the other. Instead of that, we're going to kind of rearrange them. Okay, so we're going to introduce that the layers can not only have length, which length is essentially the number of hidden units there, hidden units or hidden neurons there. Instead of length, now they'll have width and depth. Okay, so width. So in addition to length, you have width and depth. Okay, now it's becoming a three-dimensional output. So what we're trying to do is to go from vectors to vectors to vectors, which is what was happening in feedforward neural network, to tensors to tensors to tensors. Okay, or 3D arrays to 3D arrays to 3D arrays. Remember, the input is a 3D array. Our images are 3D arrays. So it's kind of natural to kind of gravitate towards, okay, why should I produce a vector in between? Why can't I just produce a 3D vector? Sorry, 3D array. And that's that's what we're trying to do. And this depth is not the same as the number of layers. So number of layers in feedforward network is not related to this depth that I'm talking about here. Let's see how we do it. Okay, at least giving going from a length to a width and height is kind of somewhat easier, in the sense that let's say we have this hidden layer. Let's say there are 400 neurons here. Simplicity. These 400 neurons, I can just rearrange them as 20 cross 20 neurons, right? Still same number, right? So think of that's what we're doing here. So this hidden layer, we're just arranging it as one neuron below, one neuron next to each other, so that they're just rearranged. Then nothing has changed. Okay, the connections are still the same. Each neuron is looking at everything before it, in the sense that each neuron is connected to all the inputs. For example, so let's say the input is 10,000. Okay, then let's say that we also rearrange the input to be 100 cross 100, okay, which leads to 10,000. Then each neuron here is still connected to all inputs, because it will have, each neuron is related to 10,000 weights parameters. Okay, we just didn't do anything. We just rearranged from just length to width and height. Okay, we haven't done anything yet. And this output, what we're going to do is just keep it as a vector, but we want to kind of arrange it this way. So let's not focus on this, but it's just a vector. Okay, so let's keep it as a vector for now. Okay, not doing much there. So now comes the interesting part. We're going to now add depth, okay, into this architecture. And by the way, if something is you're not following, I'm going to give two views. We're starting with a layer view, just rearranging neurons to get a sense of getting a sense of tensors to tensors perspective, and then we're going to look at what exactly each neuron does in this new model. Okay, so because once you know what each neuron does, you can say what is the full function here. So let's do that. So this was easy, just rearrangement of neurons, the left side. Now we're going to add some depth. Okay, so now what's going to happen is from layer to layer to layer, or from stage to stage to stage, we're going to go from a 3D box to another 3D box instead of a vector or a slice like this. Okay, think of this as a slice of bread. Here we have multiple slices of bread. Okay, so in fact, you can think of this as a matrix, right? Remember, a hidden vector is just is a vector. If we rearrange it, it looks like a matrix. What we want is actually a collection of matrices. Okay, and that's what a tensor is. So we actually are going towards, we want to get to this. Okay, and this is what's going to lead us to having less parameters. Okay, remember, a feedforward network has too many parameters for images. We're going to reduce that in a few minutes. So we want to get to some depth here. Okay, so if you really think in terms of 3 dimensions, right? So everything, if you want to think of everything in 3 dimensions, input as 32 plus 32 plus 3 is a tensor. Output, you can actually add some redundant dimensions, 1 cross 1 cross 10 if you want, and so output is also a 3D tensor, right? 3D array or a tensor. And so we want to make all the hidden outputs, okay, intermediate quantities, also 3D arrays or tensors. Okay, that's what we want to do. So previously we had something like this. This is just showing a 2 hidden layer network instead of 1 hidden one, but we're going to make them into same. First we're going to rearrange them into like, let's say, slices, matrices, and then we're going to add depth into it. Okay, but if this was this is the second example where it just has an extra hidden layer. In this case, if we just rearrange the neurons, every neuron is still looking at everything from its previous layer, right? So, for example, the first neuron with the first hidden layer looks at everything on the input. Okay, everything means, remember, input has 32 plus 32 plus 3. It's too many numbers. So input already has a depth. Okay, we're going to create some depth in the intermediate quantities, intermediate layers. So how do we add depth? Okay, so so this is what we want to get to. So input already has some depth. Okay, three matrices, one after the other. We want to add some depth, like maybe 5 matrices. Maybe in this example, yeah, in this example is 5 matrices. Here we want to get to something like this. There's still a rearrangement of neurons. Okay, just like before. So think of each circle here as a neuronal output, if you want. Okay, so there's 5 neural outputs here. There's 3 in length and maybe 2 in this direction. Height and width are like 3 and 2, but depth is 5. Okay, so we want to get to some arrangement like this. And we do that, and we'll show you how to do that. But before that, let me just even give it a name, because we're going to do this transformation in a second. But we're going to refer to that as a convolutional layer. Okay, convolutional layer essentially goes from a 3D array to another 3D array. So this is a 3D array. From here to here, there could be also convolution layer. So it just goes from, takes a 3D array as an input and produces 3D as an output. Okay, that's what this layer is. And in addition to that, we'll also look at a couple of other layers. One of them you have not seen before, which is called a pooling layer, and that's why we are using the acronym, this acronym. And the last one is a fully connected layer. We've already seen it before. It's just, you know, Wx plus b of whatever was, you know, whatever is the input, just do a linear transformation, and that's the output. That's a fully connected layer or a feedforward layer. Okay. And generally, CNNs, the convolutional neural network models, they just stack these layers in various ways, and that's why the layer point of view is useful. In feedforward network, layer point of view was not so much useful, because whether you rearrange the layers, it's still linear layers. It's not going to look different. But here, the moment you introduce 2 additional types of layers, then you can actually have a con layer followed by a fully connected layer followed by a con layer if you want. Like, you can mix and match these layers. Okay, and think of them as like composition of functions. Essentially, if you're from a more applied math or math background, you're just composing functions. Okay. So we'll get back to that layer view and this rearrangement in a second. But if we had such an object which would go from a tensor to a tensor, then you could have an example architecture or a model definition like this. You could go with an input, start with an input image, pass through a con layer, you get some tensor, you will pass through a pool layer, you get some other tensor. Maybe you can just vectorize the tensor and apply a fully connected layer, and then you get 10 scores or 10 score values, with hopefully score being high means that class, and then that's your model. Okay. So here I'm just saying exactly what this is. It turns out in con layer, neurons are going to be exactly like regular feedforward neurons, with one change, which I will say next. But as I said, con layer can produce a different tensor. Okay, it produces a box. So let's say the box is 32 cross 32 plus 12. Okay, so we have to give some dimensions to the box. I just gave some arbitrary dimensions here. And then pool is also a layer which takes a box in and produces a cuboid or box out. So let's say it produces a box which is 16 times 16 times 12. Okay, here I'm just going through very high level some input output sizes. Okay, and we'll actually get into what the layers are in a second. And then what you can do is, okay, 16 times 16 times 12, I can just vectorize it. I'll have whatever is the number product that is, and from that vector I want to produce 10 scores. Okay, that's clear. Okay, let's actually see at the layer level. So what we're doing is take an input, pass through 2 layers or pass through 3 layers and produce scores. Okay. Some layers will have parameters. So fully connected layer, clearly there's a W matrix and a B vector. Similarly, con layer will also have parameters that we'll see next. But in between, pool layer may or may not have parameters. Here I just said may not, but sometimes they may have, but they may not. Okay. And what we want to do is optimize the parameters of this layer, optimize the parameters of this layer, optimize the parameters of this layer, all of them simultaneously to minimize the loss so that you get good prediction accuracy. Okay. So now let's actually come back to this con layer that I've been teasing, I've been mentioning it a couple of times before. So what is this con layer? So this con layer has parameters. So just a fully connected layer has parameters. Con layer will also have parameters. And all we know so far is that the con layer takes a tensor as an input and produces tensor as an output. That's all we have kind of quantified. We haven't said how, and generally for every layer, if it produces an output, let's say it's a tensor, then every cell of the tensor, you can think of it as an output of a neuron. Okay, so that perspective doesn't change, and we'll come back to that perspective later. But every, like in the fully connected case, if we produce 100 numbers in the hidden vector, then every coordinate is essentially a neuron. Here, if you produce a tensor, every cell in that tensor is essentially a neuron or neuron's output, and so there's a neuron backing it. Okay. Now let's come back to this con layer. The con layer has parameters. Let's call those parameters. We're going to arrange those parameters into sets. Okay. What is a set? Set is just a collection of objects. So let's say we have parameters. I'm going to think of these parameters as sets of what are called filters. Okay. Again, it's a new name, filter. Set is, everybody knows what a set is, but so it's a filter. Okay. So we're going to call these parameters. We're just going to rearrange. So we're just defining the parameters of this con layer in terms of sets of filters. Okay. Sets is fine. What is a filter? A filter is nothing but a linear function or a linear transformation. So filter is nothing but some W or WX, if you want. W and a B, if you want to think of it that way. So a filter is nothing but a linear function, which means it's a W comma B pair. The parameters of the con layer are a collection of W comma B pairs at just this layer level. Okay. And what does this filter do? It produces, each filter produces a single number. Okay. And the parameters of this filter, so the parameters of the network, parameters of the layer are just the parameters of these filters, just collected together. Okay, and these parameters of the filters are what we're learning when we train, when we update the parameters of the con layer. Okay, so here's an example. Let's say the first layer. So let's say we have the input and we are doing the first con layer. We are applying a con layer to the input itself. Okay, so the input is a 32 cross 32 cross 3 array, and we're going to produce an output tensor or some 3D array. Okay, so let's say there's a filter. We're going to define the filter to be 3 cross 3 cross 3 dimensional. Okay, which means that 3 times 3 times 3, 27 numbers to define that filter. Okay, so since it's a filter has this dimension, which means the filter is also looks like a tensor. So it also has width and height and depth. Okay, so let's call it filter depth just to kind of not keep it like specific to this. So the filter looks like a block. Okay, so it's 3 cross 3 cross 3 like a Rubik's cube, if you want to think of it that way. Okay, now the way we're going to remember, the con layer is supposed to produce a tensor given an input tensor. Given an input image, it has to produce some tensor, right? Now we said con layer is defined using these sets of filters, and we said one filter can look like a Rubik's cube. Okay, how do we produce a tensor using a Rubik's cube or 10 such Rubik's cubes? Right, that's the question. Right. So the way we do it is we take one of these filters. Let's say this 3 cross 3 cross 3 filter. One of these. Let's say we said we had a set. So let's say we have a set of 10. We take one of them, and we actually do what is called a convolution operation, or we convolve. Okay, but instead of calling it convolution operation, let's just call it a matrix multiplication, if it makes it simpler. Because at the end of the day, computationally, it's just a matrix multiplication, or it's a tensor multiplication. So what we do is we take the filter and we convolve the filter with the input. Okay, and I'll show a diagram in the next slide, so it's kind of more clear. But I want to first give the English definition and then look at an example. So we'll convolve the filter with the input across the width and the height of the input. Okay. So let's actually see the picture here. So let's say, for simplicity, let's say the image is a black and white image. Okay, which or grayscale image is the same thing. And so let's, for now, just for now, ignore the depth part of the image. Okay, it's not a color image. Okay. So here's an example of what's happening. So let's say we have the 3x3 filter, right? So because the input doesn't have a depth, okay, we'll also say that the filter doesn't need to have a depth. Okay, only when the input had some depth, we need the filter to have depth. Okay, that's one constraint, and we'll talk about the constraints in the next slide. But here's an example of a filter which is in the red. Okay, so the red numbers together form a filter. Okay, so 1 0 1 0 1 0 and 1 0 1. Those 9 numbers form a 3x3 filter. And the way I'm calling this convol operation or multiplication operation is that, let's say my image size is this, right? It's 5x5 image. Okay, so image means it has a bunch of numbers in it. These bigger numbers are the entries in that image. Okay, since it's a black and white image, an image is nothing but a matrix. Okay, in this case. Okay, convol operation just means I'm going to start with the top left. I have this 3x3 matrix. I'm gonna put one the filter on top of the image and just do element-wise multiplication. Okay, of the corresponding coordinates. Okay, since I'm on the top left, I can only cover a 3x3 region. I'm going to multiply element-wise, and then I'm going to add the numbers together, whatever I got, and that's this number. So you can see that, right? So I have 1, 1, 1, and 1. These are 4. And so I add them together. That's the 4 I got in the top left cell at the output. Okay. Now here's the interesting part, right? That's why it's called convolutional operation. So now what I'm going to do is move one step to the right. Okay, mechanically. And so I'm going to occupy this region, this 3x3 region, and again do element-wise multiplication and aggregation or summing, and that's going to be my second number. Okay. Again, move to the right one step, and I'll get the third number. Okay. Now I've exhausted the first 3 rows. I'm going to move one step to the bottom, go to the leftmost side. These 9 numbers, right? Get the second number and so on. Okay. So don't worry about why I'm getting only, why do I have 5x5 image and why do I have, like a 3x3 matrix here? We'll talk about that soon. But that's what the focus of this slide is, just to say you can slide a small filter on top of a bigger matrix, or basically an input image in the sense, and get some output numbers. Okay, so now is a good time to click on this and go to that. Yeah, so this, so by the way, this filter and these notions of filter, convol, and so on are from signal processing literature. Okay, so if you have done electrical engineering or something, you would have heard of these names. So here's an example, right? So here's an example filter. So actually, I don't know if same filter is there. Nope, I don't know which filter that one is. So okay, let's pick some matrix here. So okay, this is a 3x3 matrix, right? This is an example filter. Okay, they're calling it kernel here, but think of it as a filter. So here's what the operation is, right? So I'm on the top left. You can see my cursor. My cursor is actually going to this part of the input image. I'm just saying, okay, the filter is fixed. Okay, the filter is 0, -1, 0, -1, 5, -1, 0, -1, 0. And it has a name, okay? The name is at the top. Sharpen filter, I think it's what it's called. I'm just going to go to the top left of this black and white image. The black and white image has intensities, okay? 255 corresponds to, I guess, white, and 0 corresponds to black. So you're just taking the numbers here, multiplying it element-wise with the filter, and then summing up the number. You got a 64 as a number, and that's the number at this location. Okay? I'm just gonna put those numbers, and it actually works. Okay, it's not a completely random pattern here. And if I go to the next one step to the left, so one step to the right, I get a new bunch of numbers, multiply them together. That's the second number here. Okay, so that's how I'm generating this output, by applying a filter on the input. Okay, so what is this output? Output is a matrix. For one filter, I get one matrix as an output. Okay, because it's a black and white image, image doesn't have a depth. Okay? Image doesn't have the 3 colors, or therefore the 3 layers. That's why this filter also doesn't have a depth. Okay, but if the image had depth, then the filter should have the same depth, filter depth. Okay, and then you would still have the same result, in the sense that For a single filter, for a single input tensor, you should get a matrix as an output. Okay, that's what we're getting. Okay, this and these filters have names. Sharpening, as you can see, it's sharpened the image here, and there are filters like blur. This blurred the image completely, right? Yeah. Doesn't have to be 3x3. It can be more. I mean, it can be 4x4. It can be 5x5. Yeah, I mean, if the filter is of the whole picture, then you just get one number, right? So it can't move around. You're multiplying element wise and adding up some number, then your resultant matrix is 1x1. Yeah, that's fine. Any questions about at least this operation? Okay, with a single filter, irrespective of the input depth, you're going to produce one matrix as now. Okay, let's come back here. Okay, so I mean, few things notice. First of all, filters are small along width and height. We saw 3x3 as the width and height, but you can say, as he was saying, we can have 7x7, for example, okay, or 11x11, whatever number. I mean, generally it's square. You can also make it not square if you want. Okay, filter depth should be the same as input depth. Okay, so in this example that we saw in the previous slide in the web page, there's no depth. Okay, it's a matrix. It's a degenerate tensor, 3D tensor. So, for example, input is x times y times z, whatever x and y are, like 32 cross 32 cross 3. Then filter should be, let's say 3 cross 3 is what we chose, so 3 cross 3 cross 3. Okay. Now, as we slide this filter on this input, at the first stage, it's kind of clear. Okay, there's an image, and you're actually sliding it across. But if the con layer is somewhere else, it's not, the input need not be an image. Okay, and then it need not be interpretable like this. But as we slide, we produce what is called a 2D activation map, or just a matrix. Okay, in other words, just a matrix. Okay, so it's a activation map because we'll see why it's called an activation map, very similar to feedforward networks in a second. Okay, and very similar to feedforward stages, filters weights or filters parameters, those numbers in the 3x3x3 matrix, they'll need to be learned during training. Okay, and in fact, it turns out these filters actually, especially in the first stage, they try to detect some low first order things about images, like where's the edge, where's the color, what's the color, what's the orientation of some feature in the input, and so on. Okay, and you'll see that with some images. There are some images later on we'll see. Okay, but before we do that, looking at patterns and stuff, now let's come back to the neuronal view. So we started with layer view, said okay, instead of layers looking like one neuron below the other, let's actually make them into tensors. Okay, and we said con layer is nothing but a collection of filters. So let's say I have 10 filters, then each filter is going to produce one slice of bread or one matrix, and so I'm going to put all those together, and I'm going to actually get a tensor. Okay? So at least operationally, it's clear that if I have a tensor and if I have a bunch of filters which define a con layer, then I can get a tensor out. Okay, because I can stack all these 2D activation maps and matrices together, and I get a tensor. Right now, let's connect it back to the neurons and why it's an improvement over feedforward network, because feedforward network also had neurons, but the neurons were connecting to everything, and that's why we had an explosion of the number of parameters. But here we'll kind of avoid that. Okay, so let's look at that. So for that, we just want to understand. Remember, for any layer, generally, if it produces an output, in this case a tensor, each cell of the tensor, you can think of it as an output of a neuron itself. Okay, so that means that how many neurons are there? As many as the cells of this output tensor. Okay, so we need to kind of connect. So we're going to look at what does each neuron do here. Okay, yeah. So here's the important part. Each neuron is connected to a local region of the input tensor. Okay, that's the first property, and we'll see that image in the next slide. So each neuron is connected to a local region of the input, and the spatial extent of this input region is called the receptive field of this neuron. And the depth connectivity is the same as input depth. Okay, that's last point is kind of we already saw that. So let's actually look at this image. As I said, let's say the con layer produced this tensor as an output. Okay, this is like a blue box, and let's only focus on one slice, not really slice, but like this in the depth dimension basically. I want to focus on depth dimension. I drew 5 circles here. So each circle, think of it as being produced by one filter. Okay. So let's focus on, so each circle is being produced by one filter, but that neuron is in some slice, okay, some bigger slice. So let's focus on this neuron, the one neuron here. This neuron is only connected to a small portion of the input tensor. Okay. So the input tensor is 32 cross 32 cross 3, and this filter is 3 cross 3 cross 3. Then the number of weight parameters obviously of the filter is 27. And there's also a bias parameter which I did not show in previous illustrations. I'm going to revisit, show it in the next slide. But that means that this neuron is only looking at a 3 cross 3 cross 3 slice of the input. Okay. And I'm going to connect it back to that sliding thing that we did. So basically what's happening is I don't know if I have the picture. Okay. So basically what's happening is this neuron is this number is the output of a filter operating in this part of the input tensor. Okay. If the same filter moved one step to the right, okay, and operated on a slightly different slice of the input, it would produce a neuron next to it, or some output next to it. Okay? Remember, each slice here is by one filter, and the same filter is moving around on the width and height dimension to generate an activation map, right? 2D activation map. So although all these 5 neurons are looking at the same input spatial region, they're all from different filters. Okay, so the depth of the output tensor is because each slice is produced by a different filter, but at the same time, each slice is produced by a different filter. Since the whole slice is produced by a filter, like each of the 5 slices here, the same filter weights are kind of being used for each of these regions that are being looked at. Okay. Let me come back. Let me come back to that one-dimensional diagram to revisit this. So let's come back to the layer point of view. So the size of the output tensor, as I said, depends on first of all how many filters there are. Okay, remember the column layer was a set of filters. So let's say there were 10 filters. Then the output tensor will have a depth of 10. In the previous slide, there were 5 circles that I drew, which means illustratively, I was saying the number of filters there is 5. Okay, that's one dimension of the output tensor. Now, what about the width and the height? Okay, width and the height depend on how do I slide this filter on the input tensor. Okay, if I do, if I make a step to the right by 1 unit, then that's going to result in a potentially bigger output tensor than if I did 2 steps at a time. If I jump by 2, then I'm doing less computation. So hopefully, which may result in a smaller output tensor. Okay. And also, it also depends on one last thing, which is like an extra bunch of zeros that I'll add on the input side before doing the sliding, and that's to take care of edge effects. Okay, I will revisit all 3. So let's come back to this example. So what I'm saying is, one filter produces a 2D activation map. This output size, okay, since we ignored the input depth, in the sense there is no input depth here in this example, there's not going to be the filter will not have its depth. Okay, but there's only one filter being shown here. This filter, if it moves 1 step to the right and then 1 step to the right, and that's why we have 2 cells here. If this filter said, okay, I'm going to move 2 steps to the right, then there's only going to be 2, and this last row will not be there. Okay. I think yeah. So stride is 1. In this example, going from a 5 cross 5 input to a 3 cross 3 input, stride is 1, and the zero padding is there is no zero padding. Okay. What is zero padding? Think of a situation where I put zeros here all around this image. Okay. I just, instead of a 5 cross 5 matrix, now it became a 7 cross 7 matrix. Okay. Zeros to the left, 0 to the right, zeros to the bottom, zeros to the top. Then if I start doing the same exact operation, because I have extra zeros, I'll have a In fact, I'll have a 5 cross 5 matrix here. Okay. So 0 padding equal to 1 increases the size of the output. Okay. So let me actually come to a picture first, and then I'll come back to 2 slides back. So now let's actually look at a bigger example. So here is an example where the original input was 5 cross 5, and I put 0 padding. Okay, 0 padding just means I put zeros around this input tensor, and this input actually is therefore 7 cross 7 cross 3. So now the input has three layers. Okay, first one, second one, third one got cut off. Okay, there's actually more here, but we dropped it. And now, in this example, we also have 2 sets of filters. Okay, we have 2 filters. Each filter is 3 cross 3 cross 3, right? So 3 in one slice, 3 more in one slice, and 3 more in one slice. So the filter is a 3 cross 3 cross 3 tensor, and it also has one bias, one extra number per filter. Okay. Now here, what we're trying to show is the operation of the second filter to produce one number. Okay. Remember, if there are 2 filters, then there will be 2 output activation maps. That's why there are 2 green colored matrices. Okay, so think of the second filter, which is this column, producing this second green matrix, and the first filter is producing the first green matrix. We're not focusing on that. Now, what are we trying to focus is that this filter, this collection of numbers plus this extra number, they're all sliding from left to right, and then bottom one step below, left to right, and so on, to produce this matrix. Okay, so in particular, this number 1, which is in green, is by operating each one of these 3 slices on each of the 3 input slices. How do you operate? You do element-wise multiplication, sum it up, element-wise multiplication, sum it up, element-wise multiplication, sum it up, and then sum the whole thing together, and then add this extra number, and that's this number. Okay, I'm really like decomposing the whole operation of this into like a bunch of additions and multiplications, but that's what an example with 0 padding. And here we got a 3 cross 3 matrix. Okay, that means the stride here, stride here is not 1 but 2. I do this computation, then I move 2 steps forward. So I get this as my region of interest, basically, and then 2 steps forward, I get this as the region of interest. Okay, that's why I got 3 numbers over there, because stride is 2. Any questions for this? Yeah.
So the depth of the filters basically working on each depth of the input.
Yeah, if the input had only 2 matrices here, then you only have the filter depth would be 2.
And you would only use the first depth of the filter on the first layer of the input.
Yeah, first layer of the filter, first layer of the input, second layer of the filter, the second input. Yeah. Yeah, so filter essentially, I mean, really decomposing in a mechanical way, but essentially filter operation with the matrix is just a matrix vector, or it's just an inner product going on. If you want to vectorize these things. Okay. Yes. Final numbers, yeah.
So when you
First column over here.
Sorry, I'm doing it. I took bias 0 and then I was doing it for the second filter.
Yeah, so this has a 0, that's why it's 1 here. If it had 1 here, then it would be 2. Yeah. Actually, let's come back to this other picture. Now it's gonna be helpful. Is that, remember, this is the output, and this is the same output tensor from before. The same 5 neurons. Now I've also highlighted that slice. Okay, this slice here is the 2D activation map for one of these filters. Let's say the first filter for this related to this column. So this whole slice, all these numbers are being produced by the same filter operating on different regions of the input. Right. So if this filter was looking at the top left, there will be one number here. filter move to the right, there'll be another number here. That's exactly the picture that we saw earlier. So what does it mean for a neuron to have a spatial field? Is just that if the filter is only looking at this part and producing a number, that means that that neuron is only looking at this part to compute, right? In fact, that neuron is looking at only that portion of the input and is also using those filter weights, that's 3 cross 3 cross 3 filter weights, and other neurons in this whole slice are also using the same 3 cross 3 cross 3 weights. Okay. In fact, all the neurons in this green slice are using the exact same weights. Okay. Now you can like make a connection. Oh, the whole matrix was only produced by only one set of weights, unlike in the feedforward case where each neuron had its own like collection of weights. Okay. And let's say I have 5 such filters. So it's 5 times 27. Let's say 3 cross 3 cross 3 plus maybe biases, but I'm only thinking it's a small number compared to each neuron. So when we rearranged from feedforward to make it into like a square type of thing, each neuron was connected to everything in the sense that all these input numbers were needed to compute an output at that neuron. Okay, if we just when we just rearrange from feedforward to this into a height width version of the layer view, right? Yeah. So that's where I think that's where the reduction of parameters comes from. But what is the key assumption built in by defining the model this way, by defining the con layer this way, is that if a filter is useful in one region, it should also be useful in other regions. Okay. So at a very high level, think of it like you have an image of a cat. It doesn't matter whether the cat is in the top left corner or the center or the bottom right corner. Okay. As long as there's some way to just if let's say there is a filter, it's not exactly a filter, it scans and figures out it's a cat, but it's a example illustration. But if a filter is relevant for detecting a cat, then the filter is basically scanning through the whole image, but it's only looking at parts of the image, okay, and seeing, okay, where is this cat? It's detecting a cat. Okay, then some neuron has a high value. Okay, so it's basically saying that if the filter is useful for one region, it's also useful for other regions. So let's actually compute. Let's actually think in terms of filters rather than each individual neuron doing something with the full input. Okay. And so all neurons in each depth slice or each 2D activation map use the same weight and bias parameters, and this is where the parameter reduction is coming from. Okay. So I mean, just to kind of complete the calculations, the number of filters is m, let's say 5 in the illustrations, then 5 times 3 times 3 times 3 plus 1. This is the number of parameters per filter we chose. It doesn't have to be 3 plus 3 times 3 times 3, by the way. The last 3, as I said, the filter depth is determined by what is the input tensor depth. If the input tensor had like 200 as depth, then the last parameter has to be 200. But this layer, if the input depth had 3, then this is the number of parameters you would have, depending on how many filters you choose. So that's another choice you need to make. And that's it. That's the number of parameters of this layer compared to a fully connected layer, where the number of parameters is the number of number of rows and number of columns of the W matrix. Right. So don't worry about this comment about gradients. I mean, this is like a lower level detail about, if multiple neurons are using the same parameters, and so gradients have to flow. So gradients, if you look at the computational graph, there's going to be some back propagation through multiple outputs. It's like, the computation graph will have computing some node which is connected to multiple nodes in the forward pass. And so when you bring back gradients, there'll be multiple gradients coming back together, and so you'll have to do some addition there. Okay. So you just think of it as like a minor detail related to this reuse of a filter for multiple neuronal outputs. Okay. Any questions before I give some examples? So that was the most difficult part of this lecture, by the way. So it's just to give you like an interpretation of somebody chose this type of layer definition, and what we've done over the past half an hour or so is just trying to tease apart, okay, how does it relate to feedforward network layer, and can we interpret like why it may be useful, and give some names. I mean, obviously these names were derived from signal processing literature because that's how all these technology kind of evolved, and that's why we have the names like filters and stride and padding and stuff like that. Okay, so here's a example of a con layer filters. Okay, in what is called AlexNet. Remember AlexNet from last lecture? AlexNet is the one which did really well 10 years ago, 11 years ago in the ImageNet combination. In fact, kind of the big breakthrough. And so they had a model definition where the first layer was a con layer. Okay, so since the first layer was a con layer, each filter had a depth of 3. They at that time had chosen the filter sizes to be 11 cross 11. Okay, why 11 cross 11? It's just choice that they made, right? And in fact, these days, the models that you will use in your assignments, the filter size is 3 cross 3. Okay, so because the depth of the filters is 3, you can actually visualize them. You can just do I am sure or whatever function you can use to just see what the filters look like. Okay, and they may not tell you too much. And then they chose 96 as the number of filters they want to have. Okay, again, arbitrary choice. So here, like actual visualization of the filter, you can visualize them because their depth is 3. Okay, so it's 11 cross 11 cross 3 images here stacked next to each other. And you can now we need to make sense of it because it did really well. But basically, you can think of this filters as trying to detect patterns like edges, vertical lines, color gradients, and things like that. But it's basically so if you had a filter like this, if there is a similar pattern in the image, then that filter is going to give a high value. Kind of, you can think of it that way. If the pattern doesn't match, then the numbers getting multiplied kind of cancel each other out, and you get a low value. So you can think of it as detecting edges and colors and stuff like that. But it's not just specific to a trained model. If you it turns out like many filters look exactly like this. So there's no just because they're looking like they detect oriented patterns or something. That's the reason why the model did well. Is not a strong line of thinking there. But any questions about this operation, common operation? This was literally the details, really gory details about how do you get from a tensor to a tensor, right? Through this set of filters, basically. Okay, so if there are no questions, then I'm just going to cover this last layer called pooling layer, and we'll stop there. It's a very simple. There's no complexity or depth to it in the sense that it's not a hard concept. All it's trying to do is reduce the spatial sizing. Okay, if you have an input tensor, okay, you have a box. Okay, let's say it's called 16 cross or 32 cross 30 cross 3. Let's say what we're trying to do is just shrink the height and width, keeping the depth the same. Okay, how do we do that? So, for example, here, if you had an input tensor which is 224 cross 224 as the height and width, and some depth, that's a 64, you're just kind of dividing by 2 somehow. Okay? How do you create this intermediate layer which doesn't have parameters mostly to go from a big box to a smaller box on the height and width dimension? Okay, so depth is going to be the same. So how do you do that? You just do some sort of averaging or some other simpler aggregation operation, right? So here's a example. It's not doing averaging. This is called max pool. What it's doing is looking at the face of each depth slice or each 2D activation or whatever the input tensor, like looking from the front, and just look at 4 numbers together at a time and take the max. The 4 numbers together, take the max. 4 numbers together, take the max. Okay, you don't have to take the max. You can take 4 numbers together, take an average. So you just need to reduce the dimension on the x and y or height and width axes, and this is how you do it. Okay, this is how people are supposed to do it. There are many ways to reduce dimensionality of a matrix, right? But this is one way to kind of shrink. And why do you want to do that? Is just complexity. I mean, if you don't shrink, then at some point you need to make it into a vector because you're going to have a fully connected layer at some point. If you don't shrink, then the dot vector, if you just vectorize it, there are too many numbers, and therefore the fully connected layer will have huge number of parameters. Okay, so that's the only reason why we're doing pooling here.
In pool, is it compulsory that you reduce it to half to think that
you can divide by 3? Yeah, you can take regions of 3 cross 3 and then drop it. Yeah. So these are all choices which are like not very, illuminating in terms of like what's the general pattern that you can take away from here, right? So these are design choices that people have made, right? So that's why we're just showing some examples. But if you have creativity, you can change it. And if you think that, they may help empirically without, it's just trial and error, but sometimes you may have an intuition of you should do it that way. Okay. So okay, so I guess I'll not talk about polyconnect layer. There are CNN implementations in browser. So what we'll do, what we'll do next time is actually this, since this was a harder concept to digest, we'll actually have very similar to TensorFlow.org. There's another link from the lecture goals. We're gonna look at that. That's an in-browser representation of the CNN, and then we'll kind of recap that. Okay, so there's one way recap, but I believe next lecture also is right after your assignment submission. So yeah, definitely remember that and don't be late. Okay. And if you have questions, obviously you can reach out to me. If you have questions right now, you can also talk to me. Okay, but yeah, we'll come back to, we'll kind of see a browser visualization of the CNN thing again to reinforce the concepts of today. Okay, so that's all for today.